Welcome back to Chemistry 4300. In this video, we're going to continue Chapter 3 on the kinetic theory of gases, and we're going to begin looking at Maxwell's distribution laws. Now, in the 1850s, James Clerk Maxwell was thinking about the kinetic theory of gases. He knew about Bernoulli's result, but he wanted to know more than just the mean square velocity. What he was after was the full probability distribution for the velocities in the gas. So this is the quantity that he derives. And from this three-dimensional distribution, he's able to obtain the one-dimensional molecular speed distribution and also the one-dimensional molecular energy distribution. So let's look at how he does this. So he starts out by assuming that the gas molecules are perfect spheres and that they're undergoing elastic collisions where kinetic energy is conserved. And then he makes an assumption about the distribution of velocities in each direction. He assumes that the distribution along Vx, Vy, and Vz are all uncorrelated to each other, which is a very reasonable assumption to make. And as a consequence of that, it means that he can write the 3D distribution as the product of three 1D distributions. In other words, the 1D distribution along X times the 1D distribution along Y times the 1D distribution along Z gives you the 3D distribution. You can only do this when your distributions are uncorrelated to each other. And that's a good approximation in this case. He also realized that independent of how he defines X, Y, and Z, that the distribution should be independent of the velocity. So it shouldn't depend on how you define your coordinate system. And that would mean that the final distribution should only depend on the magnitude of the velocities. So it should only depend on Vx squared plus Vy squared plus Vz squared in the end. So we have then a distribution that has to be the product of three one-dimensional distributions, and when we're done with that product, it has to be equal to a distribution that depends only on the magnitude of the velocity. This is what's called a functional equation, and this is a problem where you have to solve for the function that satisfies this equation. So unlike other problems where you solve for some unknown variable, here we're solving for the function. It's not that hard to do, and let's take a look at how we solve this. So this is the function that we have to satisfy. This is the relationship we have to satisfy, and we need to find this function. But it's not that hard to think of a function that when you multiply it times itself gives you back the function squared and with the function variables added up. And that would be the Gaussian function. So look at this carefully. So you see that the Gaussian function we can write as some undetermined coefficient a times e to the minus b times the velocity component squared. So because of this property of exponents, we know that when we multiply these guys together, these exponents are going to become added. So that's the trick, really, right? So we see that if we take this guy times itself 3 times with using I as x, y, and z, we get a to the third times e to the minus b times vx squared plus vy squared plus vz squared. Okay, that's the solution to the functional equation. Now what's left is we need to determine these coefficients, these a and b, in order to get the scale right for our probability distribution. Now one of the ways we can get started along that path is to remember that all of our distributions have to be normalized. So all of those 1D distributions integrated over all values should be equal to 1. So if we plug in that Gaussian distribution and we integrate it, then you find the only way you can make that integral go to 1 is that a has to be equal to the square root of b over pi. So we've eliminated one of those coefficients, and now we have it all in terms of just b. So next we take that normalized distribution function and we multiply them together to get the 3D distribution function, and now we have left only the b that we have to eliminate. So that's our next step. And to get rid of the b, we're going to go back to Bernoulli's result. Bernoulli told us that the mean square velocity is 3 kbt over m. So if our probability distribution is correct, then we should be able to calculate the mean square velocity from the probability distribution, and it should equal to this. But we have this unknown coefficient b, so we're going to use that to make sure that it equals that. So what we're going to do is we're going to calculate from our distribution function the mean squared velocity, which is Vx squared plus Vy squared plus Vz squared. That all times this guy integrated will give us the mean square velocity, and that must be equal to 3 kbt over m. So putting everything together with the form that we just got, and doing this integral with it equal to 3 kbt over m, we find that b must be equal to m over 2 kbt. So that's the result. Plugging that back into our expression for this guy here, we get the full distribution that Maxwell obtained for the molecular velocity. So this is the three-dimensional distribution of molecular velocities for Vx, Vy, and Vz. And you can see that this is a 3D Gaussian. So imagine this sort of spherical looking distribution fading off with tails, Gaussian tails going off in all three directions. And this distribution is centered about 0. So the maximum is at Vx equals 0, Vy equals 0, and Vz equals 0. And here you see the variance is kbt over m. So the standard deviation is the square root of that. So that tells us that the width, roughly, is going to be going as the square root of t, and it's going to go as the inverse of the square root of the mass. All right? So I can make a plot of this for one dimension, so it's going to look the same in all three directions. So I can just take one of the dimensions, let's say Vx, Vy, or Vz, it doesn't matter, and plot it, and you can see what this sort of cross-section would look like as a function, in this case, as a function of temperature. So this is using nitrogen gas, so I have a scale down here because I'm using the mass of nitrogen, and again, they're all centered at 0 here, and that the distribution, as you go from 100K to 300K to 1,000K, gets progressively wider. So it gets wider with the square root of the temperature. All right. And you can see it at 100K, it's going between plus or minus 500 meters per second. And so to go back to something you're more calibrated with, miles per hour is a little bit more than a factor of 2. So that means we're talking about 1,000 miles per hour, plus or minus 1,000 miles per hour at the edges here for 100K. So that's pretty fast that the nitrogen molecules are moving. At room temperature, then we're talking about 800 meters per second or so at the edges here, which is about 1,600 miles per hour. All right. Great. Now let's look at Maxwell's distribution law for speeds. Now to get this, we're going to go from a 3D distribution down to a 1D distribution. And the way we're going to do this is we're going to transform from a Cartesian coordinate system to a spherical coordinate system. So we know that we have Vx, Vy, Vz, and if we want to transform into a length of a vector and then an orientation, some theta and phi, then we can do that from the Cartesian components. This would be the length here, which I'm going to define as c as the speed, so not to confuse it with the velocity vector component, I'm going to use c for the speed. And then for theta and phi, we can calculate from this cosine relationship for theta, Vz over the length, so that's cosine theta, and then Vy over Vx is going to be tan phi. So making that substitution, we get the three-dimensional probability distribution here, and that is going to have this form here. So it's actually a pretty simple substitution here because all we're doing is substituting Vx squared plus Vy squared plus Vz squared and just putting in the c there. There's actually no dependence on theta and phi in the three-dimensional distribution. Now we're interested in the 1D distribution. This is still a 3D distribution, so what we need to do is to project out the theta and phi dependence and get just the 1D distribution, so from 0 out. What does that look like? And we can take the integral of this guy, which is our normalization condition, so this is integrated in spherical coordinates, so that means that integrating this overall space is an integral of the function with c squared dc, sine theta d theta, and then d phi. Remember your integration in spherical coordinates. So that integration, when you do that and just integrate out the theta and phi parts, you're left with a 1D function of the speed, which has this form here. This is Maxwell's distribution law for molecular speeds. And it looks like a Gaussian, except now, because of this integration in spherical coordinates, we end up with this c squared term here. And this is going to make this what looks like a Gaussian distribution sort of skew a bit, so it's got like a tail that goes out a little further on the positive sides. And this is only defined from 0 out to infinity, right? Because you can't have negative speeds. Speeds are just a number on, with no direction associated with them. Okay. So here's a plot of the speed distribution for nitrogen gas. Again, now this time we're looking at speed and not component of the velocity vector. So we see here's 100, here's 300, and here's 1,000. And again, you can see that they get wider as you go to higher temperatures. You also see that the distribution is skewed. So as I said before, it goes up sharply, and then it has a tail that goes out a little bit longer than it did, in terms of it. It sharply went up, but then went out a little slower. That's a skewness towards higher values. You also see that it goes to 0 at probability goes to 0 at 0 velocity or 0 speed. So when the speed goes to 0, as you can see here, when c goes to 0, the whole thing has to go to 0. So the probability of finding a gas molecule with 0 speed is 0. And that's a result that we find out of converting Maxwell's 3D distribution into the speed distribution. In terms of mass, here's a plot with 3 different gases of changing mass. So helium is the lightest, neon next heaviest, and then finally argon, which is the heaviest of the 3. And you see the lighter gas at all of these at the same temperature. The lighter gas has the wider distribution, and then the heavier gases have more and more narrow distributions here. Okay, let's keep moving on this. From the speed distribution, we can calculate other quantities. So one of the things we can calculate is what the mean speed is. So that would just simply be c times the distribution function integrated over all possible values. So let's go ahead and do that. And you should work this out. You get something like this here, which you can simplify, and you get this result here, which is the mean speed is square root of 8 kBt over pi m. So that turns out to be a little smaller than the RMS speed that we saw earlier. Okay, so that's the mean speed we can calculate here. Other parameters you might be interested in would be what's the most probable speed, the maximum in the probability distribution, and that we could get by just taking the distribution function and taking the derivative with respect to the speed and setting it equal to 0, solving for c, and you'd get this value right here. So if I plotted those 3 together, so here's a distribution function, and here is the mode, which is the most probable speed. The RMS speed is here, and as I said, the mean speed is slightly lower than the RMS speed. Okay. And if you're interested in, say, what fraction of molecules is between 2 speeds, then you could just simply integrate the distribution function between those 2 speeds. So if I had a distribution function, I want to know what fraction of the molecules are above a certain threshold speed, then I would integrate from that speed up to infinity. So that would be the area under this curve. Okay. And I think that's it for this video. In the next video, I'm going to show you this nice web app simulation by Paul Fostat, and then we're going to look at some experimental verifications of Maxwell's distribution law.